right, so this is chapter 22 quiz. Okay, the first one. Let me put it here. Okay, charged particle is observed traveling in a circular path. Okay, R. So this is a radius R. Okay, okay, radius R. In a uniform circular motion, magnetic field, if the particle were traveling twice as fast, the radius of the circle path would be. All right, so remember the equation radius. Okay, so radius equal to if I remember correctly, is, you see, the field is mv, charge and b, right? So this is radius, uniform circular motion radius. If you look at the equation, bigger mass, bigger radius, bigger speed, bigger radius, and field here is smaller. Okay, bigger field, smaller radius. Okay, all right. So if you observe, okay, so uniform, if the particle were traveling twice as fast, which means this guy doubled. Instead of v, it's a 2v. So radius will be 2r. Okay, so that's directly from the equation. Second one, a charged particle moving along the x-axis. Okay, so this is a moving along the x-axis, right? And so this is a v. Enters a uniform magnetic field pointing along the z-axis. Okay, so this is x, this is y, this will be the z, right? So magnetic field go here. Okay, a uniform electric field is also present due to the combined effect of the both field. The particle does not change its velocity. What is the direction of the electric field? Okay, so you must have a cross field. Okay, which means magnetic field and electric field perpendicular to each other. All right, let's assume this charge. We just assume it can be positive, negative, right? Assume charge is positive. Use your right-hand rule. You see velocity direction, right? So this is velocity, and then sweep to magnetic field direction. You see this is magnetic field direction, and then you see if you do this one, right, velocity sweep to magnetic field, then this will be the magnetic force direction. Okay, so in order to have this, you need electric. So this is the magnetic field, magnetic force direction on the charge. In order to make this charge no velocity change, so the balance force will be 0, which means you need electric force point up. So this is positive charge, right? How to make the electric force point up? Then the electric field got to be up, right? So force on the positive charge will be the same direction of the electric force. All right. So if you consider this is a negative charge, right? So based on right-hand rule, you see x direction of the velocity and z direction of the field. You see right-hand rule. You see this right-hand rule. Okay, just use your right hand, point to velocity direction, sweep to b direction. Magnetic force will be down from right-hand rule, but this is negative charge, so magnetic force will be up. Okay, so in this case, you need down electric force. Okay, so because this is negative charge, so electric force will be in the opposite direction of electric field, so this will be electric field. So either from a positive charge or negative charge, electric field direction will be in the positive direction of the y-axis. All right. Number 3, an electron moves with a speed. So this is speed of electron along the x-axis. Okay, so this is electron. Remember, this is electron. So this is electron negative, right? So along, all right, it enters the region where its magnetic field. Magnetic field is B equal to 2.5 Tesla. Direct an angle 60. Okay, so 60, right? So this is 60, so this is 60. All right, 60 to the x-axis and the line in the xy plane. Okay, so this is the xy plane. You see, this is x, this is the y. Xy plane basically it's on the plane of the screen on the paper. Calculate the magnitude of the magnetic force on the electron. All right. So basically, this is the interaction between moving charge, right? So moving charge here, Q equal to E, right? It's a negative charge, looking for magnitude, so you don't have to worry about direction, all right? So what's the equation? This is very simple. There's a force, right, equal to QV, BQ will be, sine theta. Theta is angle between V, right, and B, so theta. So in this example, it will be 60. Okay, so just plug in. What is Q? Q is E, because it's electron, equal to 1.6 times 10 to the negative 19 Coulomb. Actually, they already give you this. Use your calculator to punch everything out. All right. Number 4. A straight wire carries a current of 10 amps. Okay, straight wire. 30 degree with respect to direction of uniform this. Okay. Find the magnitude of the magnetic force on the. Okay, so everything here, right? So basically, let's talk about the interaction between current carry conductor and magnetic field. So equation here is this. So the force, so magnitude of magnetic force, right? So magnetic force basically is magnitude force. Magnitude, right? All right, you put everything associated with current carry conductor. So you have a current on the conductor, you have a length, right? And then you have magnetic field. And remember, it's sine theta. Theta here is a 30 degree current with respect to direction of the field, right? So this is, you see, current direction here, and this is the field, 30. That is the angle you're looking for, okay? So just plug into this equation. Use your calculator to find the solution, all right? Number 5. Number 5 is straight 1.0 meter long wire carrying a current. Okay, a wire is placed perpendicular to a magnetic field of this. Okay, so this is a wire current perpendicular. Okay, so B, all right? If a wire experience a force, okay, this one, what is the current in the wire? Okay, well, actually, the same equation asks you in a different angle. Equation here is FB equal to current carry. You see, you have a length. This length is L. Looking for current, right? And B sine theta. Theta here, you can tell it's 90 degree. Okay, sine 90 is 1. Okay, all right. So you have a length, you have a field is 0.2, and you have a force here is 0.6 Newton. Looking for current. All right, so it's just quickly current equal to force divided by length divided by field divided by sine 90 is 1. Okay, so that is the current. All right, number 6. Consider two current carry current loop. Okay, two current loop. Current carry current loop, right? Two loop, right? Okay, both are made from one strand of wire, and both carry the same current. Okay, no, current loop, right? Current loop. All right, same current I, same current I. Okay, but one has twice the radius. Okay, so one you have R. Okay, another one is R. Okay, you see that? Radius different. If the magnetic field strength at the center of the smaller loop is B, here is B, right? What is the magnetic field strength at the center of the larger loop? All right, so this one just tells you what is the magnetic field due to a current loop. Okay, And also it's a circular loop, right? So it's a circular loop. All right. Equation here is the magnetic field equal to, you see, proportional to the current. Okay, no big deal. And the inverse proportional to radius. All right. So it's a 2r. Okay. See. If this is 2, right, if it's r, so here is, if radius is r, then it's b. If we increase r to 2r, magnetic field will decrease by 2, all right? So because field and the radius is inverse proportional to the radius, actually proportional to the radius 1 over the radius, all right? So you increase radius, decrease the field. Increase radius by 2, decrease the field by 2. All right. Number 7. Okay, a wire lying in the plane of the page. Okay, so this is a wire, a current towards the bottom of the page. Okay, so this is a wire. As shown in the figure, what is the direction of the magnetic force it produced on an electron that is moving to the left directly towards the wire? Okay, all right. So first, so what's the magnetic field due to this wire? Well, right-hand rule number 2. Okay, so number 2 means this: if you have, this is the current, right? Then the field will be the curling, right? So use your right hand, use your thumb to point to the direction of current. Then the curling, or like the fingers will wind around this thumb, right? So this will be your magnetic field direction, right? So assume, make it this example. So if the current is coming out of the screen, out of this page, so use your right hand rule number 2. You see, use your thumb, point to the direction of the current. Then you see, field will be the curling field. This is your magnetic field, is curling. Okay, all right, just like that. All right, so magnetic field always perpendicular to the current. This magnetic field is due to the current this way. All right. So in this case, right, so if you use the right-hand rule, and then you can tell the magnetic field due to this current at electron's position will be coming out of the screen. You see, down, your curling field, this side of the paper will be getting into, right, and this side will be coming out. All right. So you see, this is the magnetic field coming out of the screen, and then use your right-hand rule number 1 to figure out, this is the velocity direction, right? Figure out the magnetic force on this electron, right? Right hand number 2. You see, number 1. So put your hands, right hand in the velocity direction, and then you position hand so that you can sweep to field direction. Okay, all right. So from this right hand rule, you know force will be up. Okay, so this is from right-hand rule. However, this is negative charge. So you flip this direction. So this will be the magnetic force direction on this electron, right? Directly towards the top of the page, directly towards the bottom of the page. You see, this will be the right answer. All right, number 8. 2 parallel straight wire, 7.0 centimeter apart. Okay. And 50 meter long. All right, so you see 2, right? So this is 7.0 centimeter. Okay, and length is 50 meter. Okay, no big deal. Each one carry a 18 ampere current in the same direction. Okay, same direction, 18 ampere and 18 ampere. One wire is securely anchored, and the other is attached in the center of a mobile cart. All right. Okay. So this is a mobile cart. All right. And if the force need to move the wire when it is not attached to the cart is negligible, with what magnitude does the wire pull on the cart? Okay. So this one, basically, in class we talk about this, right? 2 parallel wires. this guy, general magnetic field at this guy's location, right? So you see right-hand rule number 2, right? So you see the magnetic field current is up, so magnetic field will get into the screen at this wire's location, right? And use your right-hand rule number 1. You see, this is the field, this is the current direction, field direction, so this is magnetic force direction. All right, let's look at what's the field here. B equal to mu naught I 2 pi separation d, here is d, okay? And what is the force here? FB equal to current, right? This is current times length, you see, current, length, so current carry conductor. Magnetic field here is mu naught I 2 pi d, and the sine angle here is, you see, magnetic field, current, and magnetic field is perpendicular to each other, right? So sine 90, okay? So sine 90 is 1, okay? So that would be the answer. You just put in everything. Current is the same, 18, 50. Mu naught is given, right? So this is a mu naught, and pi, you know, right? D 7.0 centimeter. Remember, you turn that into meter, 0.07 meter. All right, just plug everything in, you get right answer. Number 9. Consider an ideal solenoid of length L, n windings, and radius B. Okay, this is radius B. L is much longer than B. A current I is flowing through the wire windings if the radius of solenoid is double to B, to 2B, but all the other quantities remain the same. The magnetic field inside the solenoid will, okay, so you have to know what is the equation for solenoid. This is called a solenoid. We call it a coil, it doesn't matter, right? Magnetic field, you have passing current, right? Proportional current is mu naught I n, little n. Little n here is number of turns per unit length. So this is also equal to mu naught I capital N divided by length. All right, you see, if you double the radius, this equation have you don't have radius here. You see, this equation has no radius. It only depends on length and the total number of turns. Number of turns is the same, length is the same, current is the same. This is the same, right? So they will be same, remain the same. It's nothing to do with the radius. All right, last one here is a flat rectangular loop of wire. All right, so rectangular loop of wire carry a 4.0 amps, is placed in uniform magnetic field B, right? So this is B, so this is your current. Magnetic field, the magnitude of the torque acting on the loop when the plane of the loop, so this is the plane of the loop, right, makes a 30 angle with the field is 1.1. Okay, so this is the plane of the, so the field, whatever field, right? So field is maybe, okay, so field may be, let me see, so if this is plane of the loop, okay, so field is, this is field B, you make a 30 angle. Okay, all right, so this is, assume this is the plane of the plane, right? Plane of the loop. All right, what is the area of this loop? All right, so here, this is very important. We know torque, net torque due to a current loop, right, equal to everything associated with the current loop. Remember, it's a current loop. Current loop, you have a few quantities. It's the current, area, and also number of turns, right? So, okay, number of turns, everything here, this is a current loop, right? And you have magnetic field B. What else? You have a sine angle. This angle, remember, this angle is angle between magnetic field, okay, normal to the plane. So this is a plane, right? Normal to the plane will be this angle, normal, perpendicular to the plane. So if the field make a 30 angle with the plane, then the angle normal to the plane, perpendicular to the plane will be 60. Okay, make you another example, right? So this, assume this is a flat surface, right? Normal to the surface is this, right? And the field here, assume this is the field. This field make 30 degree along the plane, okay? And then normal to the plane will be 60. Remember, you have to apply 60 to here. Okay, you see? This is 60, not 30. All right, so you make this is a 4. This is currently the 4, right? Area, do you have area? Oh, what is the area? We're looking for area. Number of turns is a fraction loop of the, okay, so number of, let's make it 1, doesn't matter, right? And BB is 0.6, right? Okay, so torque here is 1.1 Newton meter, right? So you have anything else, this theta is 60. You're looking for A. Plug in this equation, you can figure this out, all right? Okay, so this will be the, this will be, this is for solution for chapter 22 quiz, all right?